So we get started.
Okay.
Francesca, please.
Yeah. Okay, let's then see the final part of those lectures, which I hope I'll have time to go through primordial black holes, a bit of axion-like particles, and anomalies. So primordial black holes can be viable candidate for dark matter. They should be formed before or during inflation, and I think you have seen those introduced as dark matter candidate in previous lectures. The point is that they would act as cold dark matter, so they would clusterize in the same scales, and they could be all the dark matter in the universe, in principle, from a theory point of view, for a large range of masses, running from about 10 to the 15 grams up to 1,000 of solar masses. So the minimal mass for primordial black holes is limited by the possibility of having them to evaporate, and lighter black holes indeed could not survive till today, given the age of the universe, so they should have been evaporated by today and cannot sustain the radic abundance of cold dark matter. However, in this parameter space, you can use mostly astroparticle observables to set a constraint on this type of candidates. At the high end of the mass range, you can exploit dynamical constraints that you can set by the fact that those black holes would act as normal black holes, and so segregate in the center of, for example, galaxy clusters or dwarf galaxies, and they would modify the gravitational potential in ways that is not seen in optical observations of the stars in those objects. You can have them accreting matter, so as an astrophysical black hole does. They do accrete gas onto the center of the black hole, and the gas, whenever is accreting, has given angular momentum, and it can produce a non-thermal radiation. So you expect radio and X-rays to come from the gas accreting onto black holes of stellar masses, and by the fact that you don't find strong point sources corresponding with accreting mass black holes in different environments, then you set the constraints. Recently, also gravitational waves have been used, because you can always have primordial black holes binary that do merge and can produce merge event with gravitational wave emission associated to that. So you can look at the catalogs for binary black hole mergers, and you can look at the difference between the expectation from primordial black hole binaries, especially in the rate, and the stellar black hole binaries, and set limits on the gravitational waves. All those three types of search have a background that comes from the fact that also stellar mass black hole astrophysically produced can more or less induce a similar signal, so you have to find ways to break the degeneracy between astrophysical black holes and primordial ones. You can also use the deviation that a macro object would induce in the measurement of a passage of a star through microlensing, and here there are several experiments that have set those kind of limits. And the lower end of this mass range is where gamma rays and charged cosmic rays can have a word to say, a bit also for accretion here, but I'll focus on that part. So for black holes, primordial black holes within 10 to the 15, 10 to the 18 solar masses, what it can happen is that primordial black holes are expected to evaporate into standard model particles, and they produce this Hawking radiation, where they do emit into the environment some charged particle or some photons. So by the fact of this emission, you can relate the emission temperature, because the spectrum is almost a black body spectrum, with the mass of the black hole. They are inversely proportionally related. So the larger is the temperature of the emission, the lowest should be the dark matter, the primordial black hole mass. You can get, by using this type of injection into the environment from primordial black holes, you can get different constraints. So you can look at injection of particles into the early times through the CMB, and so you get constraint on about up to 10 to the 17 grams. You can get constraints from looking at the electron and positrons produced by a primordial black hole evaporation in Voyager data, and you can use the MEV diffuse emission that I mentioned before. So X-rays, let's say hard X-rays and soft gamma rays can be a way to probe these kind of masses and cut into this hole here, which is called the asteroid mass gap, where you don't have currently any constraint on primordial black hole dark matter. And so this is the only window really that is still available for the primordial black hole to be able to explain the whole dark matter in the universe. So it's very important to be able to cut further into this gap. And that's why it has been interesting to ask the question how we can use the current observations of integral in order to get stronger limits on the asteroidal mass gap. So as I mentioned before, the flux from evaporation of primordial black holes is given by an equation which reminds you of the one for particle dark matter, because you always have a term, since you have to integrate over the distribution of dark matter in the galaxy if primordial black holes are dark matter indeed. So there is always this geometrical term, but this time it only depends on the single power of rho, because the evaporation, you have this evaporation spectrum for one single black hole. So the geometrical factor is similar to decaying dark matter. What it changes is the spectrum, so of the photons that are injected per unit time and energy, and it is almost a black body spectrum with, as said, as long as, so you have spectra for higher masses, you get lower energies. So there is a limit in the masses that you can probe. For example, if you were to use high energy GV gamma rays, you would only be able to probe light primordial black holes that should have already been evaporated today, given the age of the universe. But if you are at the limit of the existence of primordial black holes today, so let's say 10 to the 15 grams, then you are in the realm of hard X-ray astronomy. So you can use the data from integral to look for an additional emission of dark matter into integral data. And to do that, you have to model the astrophysical background from the MEV diffuse emission, mostly come from inverse Compton from cosmic ray electrons, and also model some annihilationized positronium line that you have. You can add a signal from primordial black hole dark matter, which only depends on the spatial part of your model. And you can set limits, since you don't see any additional flux in your data. You can set a limit on the dark matter flux that you would expect from primordial black holes. And then you can recast these limits, as I mentioned when I was answering to a question before, onto your preferred parameter space and on your spectrum. So having a prescription for the spectrum, you can set limits on the fraction of primordial black hole as a function of their mass. And these are the latest constraints, the compilation of the latest constraints in the literature, plus this new reanalysis from integral, which you can see can start to cut the plane into the asteroid mass gap. So similar constraints can be derived on dark matter, and this really makes the point that an MEV instrument that improves the sensitivity of integral can not only help for sub-GeV dark matter and also axion-like particles, although I haven't mentioned that, but it also can help a lot for primordial black holes. The other way in which you can close the gap coming from the right part of this plot is by improving on microlensing, and especially with LSST, you do expect to go down to, let's say, 10 to the 19 at least grams in mass. So this was everything I want to say about primordial black holes, and now I'll move to the realm of axions and axion-like particles, which are not necessarily related in what I'll be talking in the following to the dark matter problem. So you have already axions and axion-like particles introduced by Tracy, but let's remind here what are the most interesting pheno characteristics that are relevant for more independent searches. So the axion, the QCD axion, from a pheno point of view, has a real strong relation between the mass and the coupling constant to the photons. And in general, the axion coupling with the standard model particle go through the coupling with the FF dual, so with the photons, and also with some fermions. So you have this FA that relates the coupling strength of the coupling of the axion with the photons, and then you might have some additional coupling with, for example, electrons or nucleons. In many models beyond the standard model physics, you have the prediction of axion-like particles. And those axion-like particles do not really have to solve the strong CP problem, but from a pheno point of view, the Lagrangian has this fundamental coupling with the photons, which is built in the same way as the one for the axion. In the low, and then you can have other terms very similar for the coupling with electrons and nucleons. So from a pheno point of view, if you take the low energy limit, the axion fundamentally couples with the electric and the magnetic field. And so the coupling with photons can go through the direct coupling or direct decay of axion-like particles into two photons, or whenever you have an axion in a strong magnetic field, it can convert into photons. And the same, of course, for the photons. If you have photons that are fields, strong magnetic fields, if the axion-like particles are present, they can be produced by this kind of Lagrangian interaction term. And the same is true when you have an electric field and a magnetic field. They can source axion through the same Lagrangian term. So all those three terms give you a rich phenomenology to look for axion-like particle in high-energy astrophysics. So let's have a look at the conversion probability of these of axions into photons and back in the presence of magnetic fields. So if you have homogeneous magnetic field, you can write down the equation of motion, which is an Schrödinger type of equation, where you have a vector where you have the photon polarization and the axion field, and then this mixing matrix here contains all the couplings with the different terms for the axion photon conversion. So you can simplify. Those terms can be written as a function of the most relevant quantities, which are the magnetic field, and only the transverse component to the magnetic field is relevant. The coupling of the axions with the photons, the mass of the axion, and then there is a term which is related to the dispersion into the medium of free electrons. So if you want to work out very simply in two dimension what is the probability of conversion, then it has a very simple expression, which is very similar to what you might have seen for neutrino oscillations. So there is a term which is related to the mixing of the axion with the photons in the presence of a magnetic field. And this term, delta I gamma, only depends indeed on the coupling and the transversal magnetic field. And then you have an oscillatory sin term, which relates to a fundamental energy scale. And this fundamental energy scale defines which type of oscillation behavior you can have between the transition of the photons into an axion. So if you are well above this critical energy, you are in the so-called strong mixing regime, where the probability of conversion of photons into axions is maximal, or axion into photons. And if you are at about the critical energy, you are in the oscillatory regime, where this oscillation is relevant, and it depends. So the oscillation where it is effective if the oscillation length is of the order of the coherence length of the magnetic field. So you can exploit this kind of phenomenology in order to set constraint on the parameter space for axion-like particles, which is the one shown here, where you have the axion-photon coupling as a function of the axion mass. I will just dub it axion wherever I talk about axions or axion-like particles. But here, this strip in yellow is the prediction for the QCD axion, which is a very narrow band in this whole parameter space, because you have a strong relation between the mass and the coupling given by the CP. Symmetry break. So you can try to cover this parameter space with different type of astroparticle and lab experiment. Here is, for example, the limits from the solar helioscope at CERN, CAST, which sets the stronger bounds on axions, on axion-like particles from a lab experiment. You can have some constraints from cosmology, here for heavy axion-like particles. And what the realm of high-energy astrophysics is rather this window here for low masses, so below the micro electron volt, and high coupling at the level of CAST, but here is still a completely unexplored parameter space. But you can also exploit X-rays, and there you can really probe dark matter axion-like particles by looking for lines that from the decay of axion-like particles into two photons. So let's have a look at how axion-like particles can be produced, because I've said that those axion-like particles do not really need to be related to the dark matter in the universe, because of this interaction with photons and this Lagrangian term, they can be sourced whenever there is a strong plasma and strong magnetic fields. So this is what happens, for example, in the core of core collapse supernovae, where you have the photons, the thermal photons in the supernovae that fills the electrostatic potential of the nuclei and can convert into axion because of the high densities and temperature reached in the core of the supernovae. So you have what is called Primakov effect. So you really only the axion to exist in your theory of nature in order to be produced in the core collapse of supernovae. And how does the signal look like? So you have a burst of axion-like particles which are produced during the explosion and the collapse of the star. This is the rate of production of axion-like particles as a function of energy for a typical supernova progenitor of 18 solar masses. For different times form the pulse bounce. So you see that is a time-dependent signal, and you can work out then what is the flux of axions produced and received at Earth. So this is just suppressed 1 over d squared if the supernova is galactic, or you have a redshift-dependent term if this is an extragalactic supernova. So then once the axion-like particles are injected into the medium, what it occurs is that they felt a magnetic field from our own galaxy if this is a galactic supernova. So there is this conversion taking place, again, from axions produced in the supernovae and into photons. So, and in the end, we do receive the photons into our telescope, and we can model what is the signal that you would expect from this kind of process. So the conversion can be worked out fully numerically in 3D, but it depends mostly on the coupling and only on the coupling, on the transversal magnetic B field, and on the distance of the objects. So there is a fundamental degeneracy between the coupling and the magnetic field. So you need a very good knowledge of the magnetic field in the galaxy if you want to break this degeneracy, because otherwise you are only really sensitive to the product of the coupling times the transversal B field. And how the magnetic field in the galaxy is modeled and is observed, and what are the observational constraints. This is all subjects for another lecture. But there are quite good models, especially now with Planck, and even more so will be with future instruments like SKA. So once you produce those axions and you have a prescription for computing the probability of conversion of axion-like particle into photons, you can derive what is the gamma ray flux. And if the axion-like particle are massless, this probability of conversion does not depend on energy, and you have a one-to-one correspondence between the energy of the emitted axion-like particle and the energy of the final observable photons. So, and this is again in this domain of 100 MeV, so where we have this very nice MeV sensitivity gap. But yet we can still do something with Fermilat because it has some sensitivity down to 100 MeV, although with high systematics. So I mentioned that we can leverage on two features of the signal. On the one hand, we expect a very strong time dependence of the signal because it's a burst, and we know how to model the signal in time. It's about a tenth of second burst of axion-like particles produced, and also we need that it should be peaked, a signal that should be peaked between 60 to 80 MeV. But then, what is really the rate to see a supernova, a core collapse supernova into your detector? Well, this you have to be lucky that, first of all, the supernova should be in the field of view of your telescope, and this reduces a bit the chances to see a signal. Nonetheless, something has been done by looking at the non-detection of a gamma-ray signal from supernova 1987A. So there was a supernova exploded in more than 30 years ago, and it has, there was a mission flying, the Solar Maximum mission, monitoring the sun, that apparently could have received some photons from this kind of event because it was in its field of view, although really tangentially. So by the fact that you haven't seen any signal of photons coming from the direction of supernova 1987A into this detector and on this satellite, then people have set constraints on the coupling versus mass, which are the leading constraints on this part of the parameter space. And what you can also do, however, those are a bit uncertain because, as I said, so it's not very clear what were the systematic uncertainties on this kind of detection, since this detector here, this gamma ray spectrometer, received the photons from supernova 1987A only from the side of the detector, and there are some systematic uncertainties which is really hard to assess given the fact that the mission is not any longer flying. So what you can also do is to look for extragalactic supernovae. So there is a bit more difficult to get the timing right, because it's important, as I said, the time dependence of the signal, and so you have to rely on optical determination of those objects that can give you a clock on when the explosion has set on. And you can look in Fermilat data for time-dependent bursts that would be associated with these known extragalactic supernovae, and you can set again a bound by not having seen any transient event from the direction of these optically characterized supernovae. What you can also do is to look for the cumulative emission of all core collapse supernovae in the universe. So you need a way to compute the cumulative signal that you expect by convolving your single supernova expectation flux with how many supernovae as a function of redshift you do expect to form. So what is the star formation history of the core collapse supernovae? You can do that and you get constraints which are at the level of the ones from extragalactic supernovae. In the future, what are the perspectives to see a core collapse supernova which explodes in our own galaxy and can lead to an ALPS burst? This was work done by Mayer and collaborators in the past. As I said, the leading constraints in this parameter space is supernova 1987A, so there is quite a large parameter space that can still give you a sizable flux of axion light particles into the Fermi-Lat detector. And if you also take into account what is the probability for the LAT to be in the right field, to cover with the field of view, the spot of the supernova explosion, then you can get this sensitivity line, which means that you are sensitive to, for example, the gamma ray signal that you come from a core collapse supernova Alps burst if the coupling is around 10 to the minus 13 GP to the minus 1 for masses at around the nano electron volt. And the same game can be played with nearby red giants that can soon go into supernova state, like Betelgeuse. Main sequence. Besides having the production of axion light particles in core collapse supernovae, what you can also do, as I mentioned, is that whenever you have photons produced in an environment with strong magnetic fields, those photons can convert into axions. And we have plenty of strong sources of gamma rays because we do detect them. So like the jets in strongly powerful acting nuclei, star-forming galaxies, but also galaxy clusters. So so those sources we know are gamma ray emitters and are also strongly magnetized objects. So you have a production of photons through, for example, PP or P gamma interactions, which is your in situ production or primary production. And then if you have strong magnetic fields, as observation would point to, what can happen is that if axion light particles do exist, there is a finite probability of conversion of your produced photons into axion light particles. So you can actually compute what is the expected flux of axion light particles that is then emitted into the intergalactic space as a consequence of this kind of interaction. So what happens as those axion light particles then is that they travel almost unimpeded into the intergalactic magnetic field, which is anyhow very low, while the photons, if you remind from yesterday's lecture, would get absorbed by the EBL. So having this kind of process, what you do expect is that while photons would be absorbed by the ABL, the axions are not. So you have, and then they reconvert back in our own galaxy. So you have an extra terms of photons that you wouldn't expect if you were not to have this transition of photons into axions. There are some uncertainties on the characteristics of the medium where the photons into axion conversion take place. Depends, of course, if this is how the jet is powered. It depends about the interstellar medium of the galaxy where the jet is occurring, or the star formation, if this is more bursty or is a normal galaxy. So are estimates and constraints that are affected by large astrophysical uncertainties. You can do something also similar for galactic objects, like pulsar and supernova remnants, which would inject inject photons that convert into axion-like particles and back while traveling into the galaxy. And there are two main features here, so that depends on what is the energy that you are looking at. So this is how the probability of conversion behaves as a function of energy, something that I've shown before. There is this sin squared term that below a critical energy is behaving like with oscillations, and above this we are in the strong mixing regime. This critical energy depends on the properties of the axion-like particles, so the coupling and the mass, but also on the properties of the environment, so the plasma frequency, which is related to the free electron density, and the magnetic fields. So depending on where this energy, critical energy is, you can have different phenomenological observables. If you are below the critical energy, you do expect that since the probability depends on energy and gives you some oscillations, then also the spectrum observed, which is nothing else than the spectrum, the intrinsic spectrum times the probability, the conversion probability, also gets some oscillatory behavior. So you have some feature, some oscillation feature in your energy spectrum that you can look at. And if you are in the case of the strong mixed regime, as it is the case for extragalactic objects, what above the critical energy, what you do expect is this extra component in the photon flux because ALPS are not absorbed while photons are. So this critical energy, as I said, depends on the environmental parameters. So let's have a look at some numbers. If you have a galaxy clusters, you have a free electron density of 10 to the minus 2 centimeters cube, and the magnetic field of the order of the tens of microgauss. In our own galaxy, depending on where you are, you have a slightly higher electron density, but a lower magnetic field. Again, it depends spatially on where you are. If you look more to your source is a galactic center or somewhere else in the outskirts of our own galaxy. So depending on the mass for a fixed coupling, you then expect these oscillation features to occur at around the KV energies if you have masses of 10 to the minus 12 electron volts, or even TV energies if you have masses of the axion-like particles at the order of the microelectron volt. So it means that depending on the axion-like particle mass, you do expect oscillations in the spectra at different wavelengths. So you can probe different parts of the parameter space by looking at this oscillation behavior. But what you need always to have is a very strong and powerful source, because in order to look for spectral features in the spectra of high energy sources, you need a very good spectral energy distribution, so very good spectral energy resolution. And to do that, you need bright sources. You cannot do that with faint sources where you have only a few counts and you cannot really build a precise spectrum. So you need bright gamma ray sources. The closer is the better. Ideally, because there is this suppression of 1 over d square, but in case of axion-like particle, the distance is compensated by the fact that you also need long distances in order for the conversion to take place. So what you really want to is that the axion-like particles do travel along a line of sight where you have strong magnetic field. So especially for galactic objects, you want to analyze them if they are, for example, across few spiral arms where the magnetic field is the most intense, in order to maximize the conversion probability and the number of oscillations that you can see. You can do this type of searches for spectral irregularities with different type of objects. As I said, you can look for galactic and extragalactic. The idea is similar in a sense that you define your source of interest. So this is an astrophysical source emitting gamma rays, which is defined by a longitude, latitude, and a distance. And then you build your spectrum in whatever energy band you prefer. So this is, for example, the spectrum at GV energies of the Perseus cluster, so an extragalactic object. These are the data from the LAT, where you only have upper limits at very high energies. And then you perform a fit with and without axion-like particles. You compare the two, and then you can either claim a detection for spectral irregularities due to axion-like particle conversion to photons, or just set upper limits if you don't find any signal. So you see that for this type of, so this would be for masses around the nanoelectron volt, a bit more. You would expect to see these oscillations in the spectrum if you were to have axion, but you won't if you don't have this kind of conversion. So you have a smoother spectrum. So you can then define your preferred statistical way to identify this type of spectral irregularities in those very high energy spectra. How to choose the target? All of them have pros and cons. The galactic target are quite good because they only require the modeling of the galactic magnetic field, which we know a bit more than instead going into extragalactic objects where we know a bit less, and we need to model different components of the magnetic field, in particular the intercluster medium. However, for galactic objects, the strength of the signal depends on where the galactic object is located, because if it is a very nearby object which does not cross any spider arms, it didn't really, doesn't not have the length and enough magnetic field in order to convert, so we might not see any signal. While if it is located behind some spiral arms, eventually better too, then we do really to expect to see the oscillation pattern very clearly. There are systematics for galactic objects which are related on the one hand on the magnetic field, but also on the galactic gamma ray diffuse emission. While the extragalactic objects only really depend on longitude and latitude, because then they are very distant, and so they have all the length in the galactic magnetic field to reconvert back and forth into axion-like particles, and typically are the objects that are determined with the highest signal-to-noise ratio, so for which the spectral distribution is very precise, and you can really look for this kind of spectral features. Another way to look for axion-like particles, as I mentioned, so the rather fino side of this kind of energy-dependent probability is to go in the strong mixing regime, where you don't have any longer this oscillation behavior, but you do expect that once axion-like particles get produced in high energy sources, then they travel unimpeded into the extragalactic medium, and they reconvert back on Earth. So you have that the intrinsic flux for a photon has to be convolved with the extragalactic background light absorption. So you would expect that there is this absorption going on for photons, while if you have axions, you won't have this absorption term, and you would expect an enhanced flux of axion-like particles. So let's have a look here. For example, this is a spectrum of an extragalactic source at GeV to TeV energies. If you were to have only the intrinsic spectrum reaching us directly, you can have, for example, assume a power law here in green. With the extragalactic background light absorption, we know, given different model, how to model this optical depth, and we would expect this blue line here. And if you have instead axion-like particles, you would have some kind of absorption, but much less than the case where you don't have axions. So by looking at the maximal energy that those spectra from high energy sources can reach and where this cutoff occur, you can set a constraint on axion-like particle or even claim a detection. So to recap, you have this parameter space where high energy gamma rays play a role. At lower masses is mostly X-rays, oscillation, the absence of spectral irregularities for axion photon conversion that sets very strong constraints. In the order of 10 to the minus 10 electron volt mass is the supernova 1987A. And then for whatever is above the nano electron volt up to a bit less than the micro electron volt, you have GeV to TeV gamma rays. So all those searches are rather leveraging on these searches for spectral irregularities, mostly from galactic, extragalactic objects, like this Fermi NGC 1275, but also this search for the spectral irregularity of blazars in OC data, but can also look for more continuous and unabsorption features, which are a bit less constraining in general, as this Markarian 421. So now, how much time do I have left? 10? Yeah, fine. So in the last part, then I would to tackle anomaly excesses. I don't know if you have questions now. Otherwise, I'll take them later. There is one there.
Yes, I have a question in two slides before. Yeah, I understand you expected have the spectrum at high energy more higher than that you EBL and ABL, ALP?
Sorry, I haven't understood the question.
Yeah, I mean, the EBL and EBL mass ILP, that is the model that you fit or you expected. But when using the lab data, you expected that energy, let me see, 1 electron volts, that higher flux in that part?
So in general, so whenever you add axion-like particle, you expect higher flux with respect to the blue line.
Okay.
But there is always, so the conversion probability is finite. It will never be 1. The maximal conversion probability that you can have is 1/3. So there is always a bit of absorption from the photons that didn't get converted. So you get a higher flux, but it can never match the intrinsic spectrum.
Okay. In which source do you expect that? For example, blazar.
Yes, yeah. These in general are for extragalactic objects like whatever blazars, but also star-forming galaxies.
Okay. Okay. Thank you.
So it's typically done also with galaxy clusters.
So if you calibrate the EBL models with real data, wouldn't that already include the ALPS in the model, and therefore you cannot find them?
Yes. There is always a bit of loop here in the way in which the EBL models are actually determined, because they are determined by using a large sample of extragalactic objects and really modeling using this law here in order to derive the optical depth. So I fully agree, and I haven't seen yet a paper that tried to derive the ABL model with the axion-like particle hypothesis, which I think would be something nice to try.
Thank you.
More questions?
I have a question about the supernova that you can use to put the bounds. Are the same supernova that they use for measuring the Hubble constant, the expansion rate, or are
no.
different types of supernova?
No, this is a really core collapse supernovae, and you would need very nearby ones, so mostly the galactic ones. So supernova 1987A, for example, I think is a different type of supernova from the standard candle. Now I always get confused about 1A, 1B, and 2. But yeah, no, are not the same.
Then in the exclusion plot at very low masses, the bounds are basically constant.
Yeah.
Can we extrapolate this bound to even smaller masses, like 10 to the minus 31?
Yes, I think that this supernova 1987A goes down. I don't know if that goes down to the fuzzy dark matter regime. At a certain point, you cannot produce axion-like particle in supernova any longer. So I think one needs to look at what is the minimal max of axion-like particles that can be sourced in those core collapse supernovae. So I think there is a limit at a certain point, but I don't know exactly at which mass this occur.
Okay, thank you.
Okay, we can go on.
Okay, so then this is an exciting part because Astroparticle offers many anomalies that are unexplained and not understood. I just remind the Fermi bubble, for example, we don't really know where those come from. But I want to touch upon two anomalies or claimed excesses that have been found recently, and I am happy to talk about more of those in the Q&A session. So let's have a look at the antiproton excess. So there was a signal that was claimed back in 2014 of an excess of antiprotons in cosmic rays measured by MS at around a few GeV. this excess of antiprotons on top of the secondary predictions for production through spallation can be interpreted in the context of dark matter, and in the annihilation mass plane you would then get a closed contour for a signal that was claimed to be at the level of 4 sigma, 4.5 sigma. So whenever you see something like this, it means that here you have a detection, and naturally, if you were to derive bounds, you have a weakening of the bounds, because here you have a signal, and then you still have your constraining power of the antiprotons for higher masses. So this would point to a mass of around 100 of GeV for a cross-section, which matches more or less our vanilla expectation for thermal dark matter. However, it was then realized that there are systematic uncertainties of different kind, which reduce the hint from 4 sigma down to 2. And yet, the fact that this could have been dark matter was quite exciting. But how can we really exclude a signal of such type, and why systematic uncertainties are so relevant? So the point is that if you, let's just, for example, look at the IMS antiproton data from the same data set, or very similar to the one that was used to find the signal. So as I mentioned before, you have a very good prediction for what is the secondary antiproton flux with propagation parameters that are fixed by other nuclei through this secondary to primary ratio. And if you look at the residuals, just with a standard chi-square analysis, then what you see in the residuals is that there is more room for excess here. And this also appears if you renormalize the residuals with the covariance matrix. But is this really new physics, or is just systematic uncertainties? So the point is that there are errors in the data and in the model that are correlated on different energy scales. And in particular, you have several systematic errors that comes either from the instrumental response function, and so any energy bin does not have uncorrelated systematics, but they do have instead correlated systematics, and this was mostly, not taken into account in earlier analysis. But also the model has systematics that are correlated on different energy scales, which are related mostly to the production cross-section. So whenever you have this spallation, you have proto-proton interactions at GeV energies, but you don't have really a calibration from lab experiments that tells you that you know well the cross-section with very high precision. So these uncertainties need to be included. You have uncertainties related to the transport, see it here, but these also induce a correlation between different energies. And then you have also some uncertainties from the spallation process itself. So what are the parent particles that can induce this kind of antiproton secondary production? So, and when you include those systematics that are correlated in energy, then you actually start to fill this gap for the excess. So if you account for the residuals including systematics, so you see that the residuals that you see are well in agreement with the systematic uncertainties. And if you were to renormalize the residuals with the covariance matrix that you use for the model and for the data, then your residuals definitely look like Gaussian ones. So no excess in antiproton is the conclusion that I think is well settled now. You only have a kind of less than 2 sigma local significance for this excess when antiproton, where covariance is included, meaning that if you were to correct for trials factor from the fact that you want to look for different masses and you don't know what the mass of the dark matter particle is, then you only have a reduced significance. I won't go into the details here of the statistical analysis, but the point is that antiproton was just to mention that antiprotons are very effective to constrain dark matter, because while the secondary only depends on the propagation parameters that can be fixed by other nuclei, the dark matter signal only depends on the halo height. So this means that you can actually use only a very small uncertainty on the halo high and marginalize over it when you want to derive the bounds on the dark matter signal. So then you can set the bounds on the annihilation cross-section as a function of a mass for different data set of antiprotons. This is the 2016 data set where you have this slight weakening of the limits for an excess which is not significant. But then there was a later release in 2017, 2021 of IMS antiproton where this excess is completely gone. So the chair here tells me that I only have 3 minutes, but I really would like to touch upon the GVXS. So I don't know. I need 5 minutes, more or less, to just give an overview. Otherwise, I'll take questions. Okay, so there was this GVXS in the Fermi sky that was discovered at first at the galactic center and later on at higher latitudes. I mentioned that yesterday already, answering to a question, that the galactic center excess has a very peculiar spectrum picked at a few GeV, and also especially is very interesting because it extends up to higher latitudes. And it is consistent with something that would come from dark matter. So why dark matter could be an explanation for the excess? First of all, you want the spectrum to match the data within the systematic uncertainties, and it does pretty well for some vanilla model for dark matter. So BB bar, for example, annihilated into 50 GeV, for a 50 GeV dark matter particle, for a cross-section right at the thermal one. But above all, what's working well is really the dependence of the gamma ray flux as a function of the angular distance is in red as measured from the galactic center excess data with the expectations from dark matter annihilation. So people were very excited about that. However, it was soon realized that there can be other mechanisms from fundamental astrophysics that can be at play. And in particular, what can happen is that you always have a part of the population of your sources that are below the energy threshold, sensitivity threshold of your instrument. So whatever class of sources you have that gives you these bright spots here, you always also expect a fainter part of the population that contributes still to gamma ray emission, but you are not able to see the bright spot because simply it is too faint. This works for all population, all source classes, including pulsars. And why pulsars are relevant in this context is because they would induce, they actually have a spectrum, observed spectrum, that peaks at really at around 2 to 3 GeV. So they could explain the galactic center excess spectrum if you were to have a large population of sources that are too faint to be detected individually at the galactic center, which is plausible because the sensitivity to point sources is very much degraded in these regions because of the contamination of the galactic diffuse emission. And in order for the excess to be explained by those kind of unresolved sources, you would need, as I said, thousands of sources in the galactic bulge, which seems to be coherent with the model for the galactic for the galactic population of millisecond pulsars. However, we don't really have strong hints for the presence of this pulsar population at the galactic center with gamma rays only. There is a strong debate going on gamma ray analysis. You can ask me later. But I want to mention that if pulsars are responsible for this kind of emission, we know that pulsars do emit also in other wavelengths. So they do emit in radio, they are actually primarily detected in radio, and they do emit in X-rays. So you can run a campaign of multi-wavelength search for this kind of pulsars in the galactic bulge. So in order to explain the excess, you would need this large population of objects around the galactic center. On top of this, you would have the disk population, which will contaminate your detection with some foreground pulsars. And yet you can run sensitivity prediction to understand how many pulsars you would expect to see with future telescope in radio. And there are good prospects to actually be able to discover this kind of population with SKA. The same you can do with CTA, because we do expect a signal from the inverse Compton production of those sources. And you don't have to forget that complementary constraints from dark matter can also be a way to test the nature of the galactic center excess. So I finish here, and I'm happy to take the questions.
Hi, thanks for the very nice review. I had a question regarding the constraints on primordial black holes you showed at the very beginning. So, okay, we have this asteroid mass gap, and you said we should attack it from both sides, from the Hawking radiation and the microlensing. If I remember correctly, some years ago there was some femtolensing constraint in that region that was taken away because of some not being careful in the details of the calculation. Is there some prospect on recovering the whole constraint and totally wiping out that region in one take, or do we have like little by little conquer the region from the sides? So
as far as I recall, so indeed there were these femtolensing constraints, so if you include this finite objects effect, finite size object effect, then the constraints that you can set with current data are gone. So there was a paper speculating about what kind of instrument you would need to do GRB femtolensing that can cut out this parameter space, but you would really need to rely on new instrument that can target this window. So as far as I know, with the current prospects for GRBs and in instruments that we have, you cannot close that window with femtolensing.
Okay. I have actually a question about the galactic center excess and this unresolved population of pulsars. So I guess that besides the spectrum, it will also be important to explain the spatial distribution. So is it known that pulsars can also distribute to such,
Yeah, this was one of the first things that were tackled, because indeed, if you were to have only disk pulsars or young pulsars that are produced through supernova and that receive a large kick, then it would be very, very difficult to have the pulsars confined in the galactic bulge. However, there are some mechanisms for formation of millisecond pulsars in the galactic bulge. One is through the disruption of globular clusters that would be accreted by the gravitational potential during the formation of the bulge, and they would release their population of MSPs. So this can actually have a population of MSPs that receive very low kick velocities and then can be confined. And then there was recently another population synthesis based on another formation channel for MSPs, which is attacked in high stellar density environments, like the galactic center, which would form MSPs from the accretion, the collapse which is induced by the accretion onto the companion. This is accretion-induced collapse scenario, and can also have pulsar confined into the bulge.
Okay, thank you. So any more questions or comments? If not, let's thank Francesca again for her 4 lectures. And let's welcome Peter for the second lecture on gravitational waves.
Great. Okay, so it's great to be back. I'll continue discussing a bit about energy extraction from black holes. And the idea is that tomorrow I'm going to show you how all of this could be used if you want to understand new fundamental degrees of freedom, like axions or just scalar fields. So we saw how we could do a very special apparatus by lowering something onto a black hole and using the fact that if we place it on the ergo region, it's forced to co-rotate with the space-time. Right? This was this contraption over here. Now I'm going to tell you another version of this, which is the original Penrose process, which you can actually calculate things. So you can use this to actually do some calculation. The idea is very simple. You have a spinning black hole, you throw a grenade onto the black hole, and in such a way that when it's at a turning point, so you throw it, the guy's about to invert the motion, and at the turning point it explodes. Okay? Looks something like this. The grenade is here, and it explodes at some point inside the ergo region, and we'll understand why in a moment. And then there's a fragment 2 that poor guy has to enter the horizon. We'll also see why. Whereas another fragment, which I'm calling 1 just by convention, comes to large distances. So we receive this guy and we measure the energy of this guy. And hopefully we're even able to extract energy from the space-time because the energy of fragment 1 is larger than the energy that we put in. We can do this, okay? Now, we know how to do this, so the idea is to use the space-time is stationary, doesn't depend on time, so there's still an energy parameter, a conserved energy that we can define, and it also doesn't depend on the azimuthal direction, if you go back to the geometry. So you can still define a conserved angular momentum quantity. So you write down the 3 equations, L for the energy, angular momentum, and then the normalization. So you can do everything, right? So I'm going to throw, just for convenience, particle 0, this guy over here, starts from rest at infinity. So you're throwing things very calmly at infinity, okay? Just for convenience. This means that the energy parameter is 1. And it's useful to recall that E is the specific energy, right? It's the energy per unit rest mass of the particle that you throw in. Just look at large distances. And the same thing for angular momentum. So it's 1 for me. Okay, so if you write down the equations that you need to solve, it looks something like this. You can still express it as r dot squared. You need to go back to yesterday's lecture. It was something like r dot squared equals some potential, okay? And there you go. This is the potential that you have now. Because there's angular momentum, I remind you that A measures how fast the black hole is spinning, okay? And again, E and L are angular momentum. Delta 1 was 0 for null particles, okay? And I'm starting with a particle at rest at infinity. If I do this, assuming that the grenade explodes at a turning point and that the fragments 1 and 2 are also at a turning point, well, then it's easy. R dot is 0. I can solve for everything. Okay? So you can solve for the angular momentum of particle 0 and the angular momentum of particle 1 and 2. Okay? Of course, we haven't done anything yet. We're just solving geodesics. But now I need to relate the 2 fragments to whatever it was that I put there. Okay? And you do this requiring that there's conservation of misery, of energy and angular momentum. Okay? And because E and L are specific energies, so energy per unit rest mass, when you do the conservation, you need to take that into account. Okay? But if you do that, now you have everything to solve for the energy and angular momentum of the fragments. And you get something that looks like this. Energy of fragment 1 or 2, so I is 1 or 2, looks something like this. Now it looks a bit weird because of the minus sign, okay? There's a minus sign here that shouldn't be there, okay? And you get weird stuff. If this guy, I hope I don't mess up, if R0 is the point where particle 0 explodes, the grenade explodes, okay? If R0 is smaller than this, which, by the way, is smaller than 2m, and 2m marks the boundary of where GTT changes sign. It's what we called yesterday the ergo region, okay? The ergo surface. Now, if the explosion happens inside the ergo region, you see this guy is larger than 1, and hence one of the fragments has a negative energy. Totally weird. Okay? And because it has negative energy, then it's possible that the guy that comes out has, because you conserve energy, the guy that comes out actually has an energy which is higher than the one you put in, because the other guy has negative. You see? So you're generating energy with a simple explosion out of this because you have this ergo region in the spacetime. And you can actually calculate, so if you assume that particle 1 is the one that reaches infinity and 2 goes on to the black hole, then you can calculate things. Okay, here they are. So you know the energy and angular momentum that each of these particles carry, and therefore you also know, and that's what I'm going to do now, you also know what's going to happen to the black hole. Of course, the energy has to come from somewhere. It better come from the black hole, or we did something wrong. Okay, so I'm going to back react on the black hole because I know everything. So now I know how the mass and energy of the black hole changes because I know the thing he absorbed, right? Okay, so I take particle 2, I put it inside the black hole, I know what happened to the black hole. Well, it changed the mass and the spin in this way because this is the relation between energy and angular momentum carried by particle 2 that enter the black hole. If I define a dimensionless angular momentum, remember the angular momentum of the black hole scales like mass squared, so I'm just for usefulness. I just found this useful, okay? Small j doesn't have units, just a number between 0 and 1, okay? Well, now you just substitute here. This is a nice calculation. You can't find it in Cristóbal's paper, but you can check this correct. So now you have everything to integrate. So you repeat this process, and you see what happens to the black hole. You're trying to extract as much energy as possible by throwing small grenades onto the black hole. The black hole should be spinning down, and you can measure at the end of all of this how much energy you extracted from the black hole. Okay? So you integrate this expression. It's actually quite easy to integrate this. And you find the following. So if you start with a black hole that had a mass m0, okay, at the end of all of this, you have a non-spinning black hole with some mass that I'm going to call the irreducible mass, because I can't do anything else to this. I can't extract any further energy with rotation, at least, okay? And if you integrate this, well, then you find this expression. M squared is equal to the irreducible mass squared plus this guy, okay? So for a black hole that has 0 angular momentum, the irreducible mass is actually the mass of the black hole. That's it, because you can't extract anything, okay? But if you make the black hole extremal, max spinning as fast as possible, okay, then you're going to find that the irreducible mass squared is 1/2 of the square of the black hole mass. So you can extract 1 over square root of 2 times m out of the black hole. It's an incredible amount of energy. Okay? An incredible amount of energy. Actually, you can do something else, which is compute the change in area of the black hole as this process happens. You're throwing little grenades, extracting energy, the black hole is evolving. You can see what happens to the horizon area. Okay? The horizon area goes like this, 4 pi r plus is the outer horizon of your spacetime, plus a squared. Okay, and you find that the change in area looks like this. If you go back, so remember this expression. If you go back to this guy, okay, this is what happens to the changing mass as a function of the change in angular momentum when you do this Penrose process. So what you find is that there's no change in area. Actually, what you're doing is you're doing a reversible transformation to black holes. It's the best you can do, okay? So there's a second law of black hole thermodynamics that tells you that the horizon area always should be increasing or then stays constant. You're really at the threshold. You're doing stuff to the black hole, keeping the horizon area constant. This is great. So we know how to extract energy. We know how much energy we can extract. And tomorrow, I'm going to show you that you can extract a sizable fraction of this energy with a scalar field. You can't quite reach the 1 over square root of 2, but you're close to it. You can extract up to roughly 10% of a black hole mass, just placing it in a scalar condensate outside the horizon. Now, you might think that because there's a limit to the black hole spin, let me write it down here if I can. So C over G m squared has to be smaller than 1, okay? J is angular momentum, m is mass. Then you might think, well, I can do bad things to black holes. I can destroy black holes if I make them spin faster than this. Okay? Right? So you could possibly look for new physics out there in the universe just by trying to spin black holes up. So let's try to do that. So I'll take a spinning black hole, okay? And I'll start increasing the angular momentum of this black hole by well, the only way I can. I don't want to die, so I'm not going there to try to change the angular momentum. I'm going to throw stuff at the black hole. I'm going to throw stuff that has a large amount of angular momentum, okay? So I can do this, I can start with small point particles. I'm at a safe distance, and I'm throwing stuff, coins, with some angular momentum onto the black, well, not coins, that's a waste of money. Just stones, okay? I can calculate everything again, right? Because I know how particles move. Again, it's the same equation again. I'm at infinity. I'm going to throw lower stuff with small energy. You can do this calculation. Actually, I think it's an exercise with photons. You just shine a laser from the outside, okay? So I'm going to throw stuff with zero velocity, very small velocity. The black hole is going to spin up. Well, I take a non-spinning black hole, I start throwing stuff with some angular momentum, the black hole spins up, okay? So the question now is, what happens when I take a black hole which is spinning at this value, and I throw something with a large angular momentum? So I'll produce a black hole that's spinning at the maximum possible value, okay? And I'll try to do this exercise. Well, what you find is, first of all, there's a nice form for this effective potential. It factors, okay? It factors in this way, where the roots R1 and R2 are these guys over here. And if you stare at this expression for a sufficient amount of time, you'll realize that if you want there to be no turning points, remember you're throwing stuff, you don't want the stuff to come back. You want it to be absorbed by the black hole, right? So if you demand that there's no turning points, then the maximum specific angular momentum of your stone is this number here, 2 times m, okay? And when it's 2 times m, well, you can calculate now what is the change in angular momentum of your black hole. Okay, let's define, again, this dimensionless number, total black hole angular momentum over m squared. When you throw this stone with this amount of when you throw this stone with this precise amount of angular momentum, then the change in spin of your black hole, well, it absorbed some mass, some angular momentum, things change, right? You calculate the change, and it's exactly 0. So you start throwing stones, the black hole spins up, and when it reaches extremality, so the maximum possible value, this value, it stays there. The field equations don't let you destroy a black hole. It's really nice, okay? So you can't, there was this conjecture by Penrose, which we call the weak version of cosmic censorship, that says, well, the universe is so nice that whatever is inside an horizon always stays there, okay? We don't know if this is true, but this is one example of an attempt of trying to violate cosmic censorship. We can't do it. In fact, a few years ago, this was made with stones, small little stones that move on a fixed background. We tried to do this. We tried to violate, to destroy a black hole, throwing a huge amount of angular momentum at it. So we took 2 black holes and we threw them at roughly 75% of the speed of light. Okay? Usually violent stuff. And initially, so we were tuning the impact parameter. So we placed an impact parameter, an angular momentum in the system that was just too large. If these guys would merge and form something, it couldn't be a black hole, at least not in this framework, okay? And here's what we saw. So colors here are amplitude of stuff being radiated, gravitational waves. I haven't talked about this yet, I will. Color of stuff being given away by the space-time. And here you have, the 2 black holes are colliding, some impact parameter, okay? And they try to merge, they try to collide, but they realize, well, of course, they're not people, but the equations tell them something nasty is going to happen, okay? So what they do is they get closer together, they can't merge because nasty stuff was about to happen, so they zoom out, they orbit a couple of times around each other. They release in gravitational waves the excess angular momentum, and then it's okay to merge. So this is what the orbit of this critical motion looks like. So if you look at the red curve, I'm only showing you motion of one black hole. There's a symmetry here. Okay. So you throw this guy. Okay. It seems to want to merge, but it can't. So it zooms out, it radiates angular momentum and energy, of course, and then it's safe to merge. It forms, the result of this is a single black hole spinning at roughly 98% the maximum possible value. So good? So we seem to get stuck with black holes. Black holes are nice, they are simple, they are nice, and they are hard to be destroyed. How do we form them? How do they actually get to occur in the universe? Now there's at least 2 different ways. The canonical way is to exhaust the fuel of a star and you get just an implosion. Gravitational collapse, pressure is not enough to sustain your star and you eventually get just vacuum, okay? The second way, it's also a bit of a conjecture, but it works, okay? The second way is, actually it's related. The idea is always to place a sufficient amount of matter in a small enough space, okay? And there's a conjecture, which by Kip Thorne, by the way, which is called the hoop conjecture. And it states that, well, it states the following. Any object that you have, that you're given, will form a black hole when a circular hoop, okay, some circular hoop, of circumference 2 times the Schwarzschild, 2 pi, times the Schwarzschild radius of the object can be passed around the object in all directions. Okay? So for example, I have 2 examples here. The idea is very simple, right? The idea is We looked roughly at the Schwarzschild geometry. The horizon was at 2 times gm over c squared. So this is roughly our criteria for a black hole formation. Let's see how this works. You take the electron. The classical size of an electron is roughly 10 to the minus 15 meters. Okay, you equate just the mass, the energy, the rest energy of an electron to the energy in the electromagnetic field. We get something like this. So we know the mass. The Schwarzschild radius of an electron, given its mass, is roughly 10 to the minus 57 meters. So you build a hoop of 10 to the minus 57 meters in radii, and you try to pass it around the electron in all directions. You find that you can't. Okay? If you try to do that to myself, well, you have to build a hoop of radius roughly 10 to the minus 25 meters, so it's really tiny, and I'm way larger than that. I can't pass that hoop around myself. Okay? But we can find ways around this, right? Because everything gravitates, energy and mass are really just the same thing. So one way to get around this, to get around myself not being a black hole, is just taking another copy of myself and throwing it at me with some Lorentz factor, some boost. By the way, which boost would we need to do this? So if you collided 2 vectors, what would be the Lorentz boost of each of them need to be so that you have a black hole at the end of this? Okay, so the idea is simple, no? The idea is that the mass, what you need is energy. When you boost, your energy becomes gamma, Lorentz boost, times the mass. So you need gamma m, my mass is roughly 70 kilograms, right? Gamma m should be equal to this guy, right? So 10 to the 25 or so, okay? And if you do this for the electron, you find that, well, in the standard setup, there's no accelerator that we can use to do this, okay? You can get around this if you, use some exotic scenarios like extra dimensions, okay? But you can't do that very easily, fortunately for us. But this is always the idea. Okay, the hoop conjecture gets you some criteria to form black holes. So let me summarize my introduction about black holes, black hole backgrounds, and black holes as objects. I told you already, I think they're really amazing predictions of GR because they contain the failure of GR, of general relativity. They enclose singularities and they seem to be prone to energy extraction. There's a lot of open questions. I think I'm going to go back to this. But let me now tell you the second version of this story. Let me try to enlarge this. By the way, the reason why this looks awful is that I had handwritten notes that I had to take because this is not ideal, okay? But I think it's working. Now, we did point particles, okay? But now I'd like to look at what happens when you actually fluctuate the space-time. Not throwing point particles, but looking at what happens when I light a laser beam or I wave my hand close to a black hole space-time. How exactly do I think about this process? How do I actually handle this at the quantitative level, okay? Very good. So let me start with a simple example. I start with a scalar field, a massive scalar field. We talked about this already. So here's my action. The Ricci guy, the kinetic term, and now I'm adding, just for convenience, a mass term to my scalar field. Okay? The equations of motion that we get for this, that we should need to solve, are here. The Einstein equations with some stress tensor that you can actually get out of the action. You just vary them. Okay? And then the Klein-Gordon equation. Okay? Here, these guys, I don't know if all of you have seen this, but these are, a certain type of derivatives. Okay? Not the ordinary derivatives, covariant derivatives. So they know about the space-time geometry. okay? Now, solving this is terribly complicated because you need to find everything. You need to find the field as a function of space-time position, but that field, the field psi, your scalar field, also determines the metric, the space-time, right? Because the metric knows about this. You can do this. It takes a lot of work. I don't want to do this because it's not interesting most of the times, okay? What I'm going to do is I'll assume that my field psi, it's like this laser beam, okay? This laser beam is really a weak guy. If you shine this close to a black hole, it's not going to affect the black hole much, okay? So I'm going to think about these coupled equations in a perturbative sense, okay? I'm going to expand the solution of these equations for small scalar field, okay? Now, when you do this, so you work with psi very, very small, and you'll realize that what's feeding the Einstein equations, this term over here, it's quadratic in psi. So to zeroth order, you can place this to vacuum. This is nice because we already know the general solution of that equation, okay? The stationary solution of that equation. And the Klein-Gordon equation is linear in psi, and now you're going to get to solve this on the background that solves this equation, okay? This is nice. So let's start then with spherical symmetry. Well, in spherical symmetry, Schwarzschild is a solution, so I took care already of this guy, okay? I know the solution, I know everything. Now I'm going to try and solve this equation when G mu nu is what we saw, okay? There's just the black hole mass dependence. Still, for those of you who have seriously looked at the hydrogen atom in quantum mechanics, it's not totally trivial, right? Because you have all the angular dependence, the time dependence, and you need to solve this. It's a PDE, a second order PDE. So I'm going to do exactly what we do in quantum mechanics. I'm going to use the symmetries of my background to get rid of the angular variables, theta and phi, okay? And because it's spherical symmetry, I can, and the Laplacian still works in exactly the same way, I expand my field as this. I expand it as a series of spherical harmonics, YLM, and then some radial and some time and radial function, capital phi, and just for convenience, and you'll understand why the convenience, I divide this by r, okay? These are t, r, theta, phi are the standard Schwarzschild coordinates that we saw yesterday. This exercise is done in the notebook Scattering Scalars. You don't need to do anything, just do Shift-Enter, okay? But you should do, actually. You should do it by hand. Huh? But if you do that, you'll realize that once you plug this decomposition onto the Klein-Gordon equation in this background, you're going to, the thing that's going to come out is this very nice looking wave-like equation, okay? The second time derivative of phi, then the second spatial derivative with respect, not to r, but with respect to a slightly different radial coordinate, r star. R star is defined in this way, okay? And then minus some potential v, which I wrote here. This looks suspiciously similar to the Schrödinger equation, okay? This L plus 1 is the usual centrifugal term that you get in the Schrödinger equation. And then there's really now the effects of gravity, and if you have a mass term, this dictates how the field behaves at large distances. But it's a very simple looking potential, okay? So we are roughly done. No, I mean, this just a PDE in two variables. We know how to do this, okay? These are for scalars. Most of you might want to think, well, but, I don't really know if there's any interesting scalar out there. What about vectors? How do I do this for the Maxwell theory? Or how do I do this for GR? How do I do it if I have a tensor, a small tensor around it? Now you need to be a bit more careful So if you think about vectors, so by the way, what allowed us to get this wave-like equation was that we got rid of the angular variables, expanding in spherical harmonics, okay? But if you're dealing with a vector, for example, if you're dealing with a mu, so the Maxwell theory, you shouldn't be just expanding each component of your vector in spherical harmonics, because that's not going to transform correctly under rotations, right? You want it to be a vector, right? So you actually need to expand in the set of nice vector spherical harmonics, which you can build out of simple scalar harmonics. For example, there's different ways to do this, okay? You can take, for example, gradients of spherical harmonics. You can take the angular momentum operator on a standard scalar harmonic, or just build this dotted with the vector r, okay? If you do this, then it means that you took a scalar guy, a spherical harmonic, and you built vectors out of it. So now you should be in shape. Now you know you have a basis to expand a vector in spherical harmonics. Now I've done all the work for you, and the basis looks something like this. If you want to expand a vector a mu in vector spherical harmonics, they transform in the correct way, okay? Actually, this comes from just these three guys. There's no trick here, okay? You're going to find that the expansion looks like this. And I rearranged this because, in two different terms, because they transform differently when you do a simultaneous, well, when you do a parity transformation. So a simultaneous inversion of all of your axes, okay? But anyway, this is the most general expansion for a vector. If you want to know what the Maxwell equations look like when you insert this decomposition, it's in the notebook, but even by hand, it's sufficiently simple that you can do it, okay? Now, because they transform differently, there's two different decoupled equations for these two sectors. So the quantity A and all of these guys obey separate equations, okay? So you need to believe me that if you place this decomposition in Maxwell equations, then A is rather simple because it's only a single guy. It's rather simple to look at the Maxwell equations. And you find that it obeys exactly a similar type of wave equation than scalars, okay? Except that the potential V is even simpler, okay? It looks like this. The explicit form will be important, and I'll tell you why, okay, in a moment. If you do this for the second parity guys, these are usually called the odd sector, okay? Or if you want axial, this is the polar or even sector. If you do this for the second sector, then you need to massage the equations a little bit. I did that for you. So I redefine a master function that I call psi, which is a combination of those two entries, okay? If you plug this in Maxwell equations, you're going to find, surprisingly, the same simple wave-like equation for this polar sector, where now the potential looks like this. The potential for polar is exactly the same as it is for axial, okay? Is this clear? Am I going too fast? Yes. Now, we did this for scalars. For vectors, we had to construct these vector spherical harmonics. You can do exactly the same for tensors. Okay, so you take the geometry, a metric, and you look at what happens to this small fluctuation on top of a fixed black hole background. We call these gravitational waves if they are propagating, okay? And now this is even tougher because to build a tensor spherical harmonic, well, you need to build tensors out of scalars. You can do it in exactly the same way, or roughly the same way. The expressions look awful, okay? The notebook has all of this massaged, and there's a standard formalism from the 1970s, the Reggie Wheeler formalism, that gets the final answer. It's in the notebook, and the final answer is all of these massless fields obey the same master equation. And you can condense that in this expression. So all of these massless fields obey this equation, where S, this parameter S, is 0 for scalars, it's 1 for vectors, and it's 2 for tensors. Okay, very simple. You will notice that at very large angular momentum L, okay, this guy looks like the geodesic equation that we found for null particles. It's not a coincidence, of course, but you can try to compare. Okay, so what's the content of this? So now I know what to do if I have to solve Maxwell equations, or if I have to solve for gravitons on a black hole spacetime. But what exactly is the content of these equations? Okay, so let's first try to look for static solutions. Okay, so are there static solutions to this that describe a slightly disturbed black hole? I have a black hole somewhere, and now there's a static configuration here. Clearly, on planet Earth, there is, right? I take a spherical planet, and I'm here. I think I might be considered a small static fluctuation. Okay, regular everywhere. So the question is, can we do this for black holes? Right? Can we find small mountains or small Cardosos on top of black holes? Well, let's look at scalars. If you take, for example, a scalar, this is really just because it's simple. We take a scalar and we focus on spherically symmetric fluctuations, L0, okay? Static, so this piece over here is 0, just by assumption, okay? Then the solution looks like this. What's the problem of this solution? Well, the problem of this solution, it's not physical. It diverges at the horizon logarithmically, and it diverges at infinity in a linear fashion. So the only option that I have is to set K1 to 0. That gets rid of the behavior at infinity. And K2 to 0. That gets rid of the divergence at the horizon. And this is an example of a no-hair result. I'm not allowed to have spherically symmetric fluctuations of a scalar field, which are static, around a Schwarzschild black hole. Okay? Take L equals 1. Well, for L equals 1, I wrote down the solution. I mean, you can verify, it's very simple, okay? For L equals 1, here's the solution. And the same thing happens, right? So if you want to get rid of divergence at the horizon, K2 needs to be 0. And if you want to make everything smooth at infinity, then K1 needs to be 0. There seems to be no way around it. Actually, you can even study another aspect of black holes, which is polarization properties. You know, if you place a small sphere of some material inside a capacitor, it's going to polarize, right? I mean, charges move around it. If you try to do this, so how do we measure, how do we calculate the polarizability of some material? Well, we look at what happens to the subleading piece of the electric field. Right? For example, instead of a 1 over r squared, you get a 1 over r cubed, meaning that you have a dipole there, right? If you try to do that for a black hole, now you can do stuff. You have some leeway here. Because if you place the black hole in a capacitor of a scalar field, then you can say, well, if it's a capacitor, I'm not going to impose that this guy is 0, right? There's something at infinity. That's okay. Some other person is doing that to the black hole. I don't care. But I do need to make sure that the behavior at the horizon is smooth. So I need to fix this guy to be 0. But when you look at the behavior, the only thing that you get is a divergent behavior at infinity. There's no subleading piece that goes like 1 over r. Black holes don't polarize. Nobody knows why, okay? We just see this. Black holes don't polarize. And this, even though I'm doing this for L equals 0 and 1, it's a very generic result, okay? We can generalize this. So you take the wave equation, time derivatives are 0, you rewrite it in this way, V is the same potential that we had, okay? You integrate in the black hole exterior, but first you multiply by the complex conjugate of your master function, psi star, okay? And you'll find that you get this equation. Psi star is psi squared, it's a positive definite quantity, and on the left you get this guy. You do an integration by parts, very simple, okay? Just do an integration by parts and you're left with this equation over here. But if you require that everything is smooth everywhere, the boundary term, this guy over here, has to be 0. Okay, it's a very easy calculation. So you're left with this piece has to be 0. But now look at this. In the black hole exterior, this guy is positive, because I'm always outside 2m. Psi prime squared is positive. Psi squared is positive. And V, you didn't notice this, but V, this is so nice that we need to look at this again. V, for most of the cases, for a scalar field, V is always positive. For the Maxwell sector, it's almost always positive. Right? V for the Maxwell sector is almost always positive. It just isn't positive for L equals 0. And for the gravitational sector, so S equals 2, V is always positive except for L equals 0 and L equals 1. So this means, now we go back to this guy, this means that for almost all of the multiple fields, the only solution is psi equals 0. There's no way around this, okay? And this is a no-hair result. But black holes do have 3 hairs. And the 3 hairs are the only exceptions that we just saw. The L equals 0 electromagnetic case will give you a 0V, okay? And if you solve the equation, actually, what do you find? Can anybody tell me what you find if you solve the Maxwell equation for L equals 0? Charge. The only thing is an electric field that goes like 1 over r squared. It's smooth everywhere, it's fine. It just tells you you are allowed to add charge to a black hole. It's fine if you do that. The other 2 exceptions are L equals 0 and L equals 1 gravitational, and that tells you that you're adding either angular momentum or linear momentum to your black hole. You can do that as well. So this seems to say what we discussed yesterday, which is the general black hole can have angular momentum and apparently it can also have charge. That's good. Yeah, exactly. So yesterday we saw uniqueness results, let me call it this way, for the scalar field. These were very robust results at the nonlinear level. I call these no hair because it's only at the perturbative level. I'm taking a black hole spacetime and I'm looking around this solution. It could be that there's something else totally far away, right? And those are harder to prove. Is there any question? No? Can I take 2 more minutes? Okay, perfect. So I know what happens then to black holes at the static level. They don't polarize. It's a very generic result. And they don't admit any, well, they only admit 2 static, well-behaved fluctuations on top of them. Okay? Charge and spin. Now let's look at dynamics. I mean, I'm interested actually in how these guys respond when I start doing stuff around them. Okay? So let's go back to the wave equation. And the first thing you might do is, well, you throw wave packets at this guy, or a monochromatic wave. Let me start with the easy example. I take my wave equation, and I admit that there's a field that's a monochromatic guy. So the time dependence of my psi goes like this. Okay? If you remember, there was a second time derivative in the wave equation. So when you plug this, second time goes to minus omega squared, so you're fine. You're left with this guy. And this is an ordinary differential equation. Everybody knows how to solve this. Okay? And if you don't, it's in the Mathematica notebook. Very good. Now, we need to impose boundary conditions. That's what physics is all about, right? It's in the boundary conditions. So let's look at the boundary conditions of this guy. When R star goes to infinity, R star, you want to know what R star is. So let me remind you, if I find it. It's here, okay? So when R goes to infinity, this guy is 1, so R star is R. At infinity, R star is R. At the horizon, R star is roughly log of R minus 2m, okay? Roughly. And that means that at spatial infinity, R star goes to plus infinity. At the horizon, it goes to minus infinity. So it covers the entire axis. Okay, so let's look at the asymptotic behavior in 2 minutes. V is 0 if V goes like 1 over R squared. So it's 0 at infinity, okay? And it's 0, the potential, it's also 0 at the horizon, which is super convenient. Because V vanishes at the boundaries, the only possible asymptotic structure of the solutions look like this. So at infinity, you can have something that looks like e to the minus, well, it's the solution of this equation and V0, okay? But remember the time dependence is this guy. So if you plug this here, this tells you that this is a wave that's going towards the black hole, right? Because it's minus I omega R star plus T. And this guy is going away from the black hole. So I call it an A out and an A in piece, okay? At the horizon, well, I'm going to impose that nothing is coming out of the horizon because that's my classical expectation. You can actually show that you wouldn't have smoothness if you didn't do this, okay? So I'm going to impose always that at the horizon, stuff is always going in to the black hole, okay? So it's my possible solution here. So there we have it. We defined a reasonable scattering experiment on a black hole spacetime. I'm throwing this guy, this laser beam, at the black hole, and I have everything to calculate what the black hole is doing. This is done in the notebook. I should run it here, but I don't have time, okay? But you can show something else, because it's a very simple second-order equation without a first derivative piece. There's a theorem by Abel or Abel that tells you that there's a conserved guy, of course, right? The Wronskian. And if you calculate the Wronskian of this guy, it tells you that you have to obey this relation, okay? And this is a very physical kind of result, right? The energy that you put in minus the energy that you get out of the black hole has to be stuff that went into the black hole. It's energy conservation, right? So if you actually solve the, this is a generic result, but if you actually solve that ODE, again, this plot is in the scattering notebook, you find that it behaves like this, okay? At large frequency, you get a result that goes, so once you know all of these guys, these scattering amplitudes, you can calculate the absorption cross-section of a black hole, okay? At large frequencies, and I challenge you to evaluate the notebook at large frequencies, that's going to give you an absorption cross-section that matches, to your numerical accuracy, the absorption cross-section we saw yesterday for photons. 3 square root of 3 m was the critical radius for this. And you get this from really the analysis of the wave equation, how waves propagate here. At low frequencies, this guy goes to 0. If you calculate the absorption cross-section, you always need to divide it by omega squared. And this means that black holes have an absorption cross-section at low frequencies that matches exactly the surface area of the horizon. It's a universal result for black holes and scalar fields as well. Okay? Okay, and I'll stop here. I'll continue tomorrow with Kerr. Thank you.
Thanks for the nice lecture. I have actually a question on the formation mechanism of black hole, like this Hooke conjecture. Like, is there anything that can going on more realistically, maybe in the early universe, with magnetic fields having something like that can work?
Oh yeah, any form of energy is subjected to the Hooke conjecture. So I think up to a year or a couple of years ago, primordial black hole formation in the early universe was done just with the Hooke conjecture. Okay, you can put there a scalar fluctuation, so you prescribe some spectra for the changes that these guys have, and you evaluate when the Hooke fits your fluctuation. But if you can do it with a scalar field with a perfect fluid, but you can also do it with a magnetic field. It's also going to form a black hole.
But so will this be equivalent to the usual primordial black hole scenario where the perturbation leaves?
Yeah.
Ah, it's equivalent.
It's equivalent.
Ah, okay.
Yeah. The criteria to evaluate primordial black hole formation is the Hooke conjecture.
Okay.
Yeah.
Thank you.
Okay, more questions?
Thank you. So this null-hair theorem is always under stable conditions, right? So it basically tells you that if you have a perturbation, it cannot stay there.
Yeah.
But actually, there has to be some regime in which you perturb it and you decay somehow, right? Like this.
Oh yeah. Good. That's excellent. That's material for my first lecture tomorrow.
Okay.
So the only thing we showed was that if I impose staticity and regularity, I can't have anything. But of course, I'm free to throw a light close to a black hole. What happens to that light, right? That's dynamics. That's for tomorrow,
Okay.
yeah.
Right. I'll wait. Thank you.
More questions, comments?
We have seen what happens to scalars, vectors, and tensors. How hard are fermions?
They are simpler than tensors. I wouldn't call them simpler than vectors, but we know how to do that.
Okay, thanks.
Thank you for the lecture. You said that for tensors that parameter s is equal to 2. This is only for rank 2 tensors or for any...
No, rank 2 tensors, yes.
So in general, s is equal to the rank of the tensor.
I don't think there's a general proof of that, and I don't think this works for spin 3/2, for example. The only examples we have, so I'm actually cheating a little bit, okay? As that form of the potential describes totally the scalar and vector sector, but it only describes the axial sector of gravitational fluctuations. There's two, because there's two polarizations for gravitational waves as well. The second one is a much more involved form. Well, tomorrow I will say a few words about it, but it's not a generic result. It's convenient. I doubt it that all the massless fields can be put in that form.
Okay, thank you. Another question. You show that there is no perturbations of a scalar field. What would happen if you consider a spontaneously broken potential for a scalar field, so it has some vacuum value? Like, what would happen in this case?
Yeah, you can form, so there are examples. If you tweak sufficiently well the self-interaction potential, you can build solutions which are regular and have scalar hair. I'm going to talk about one example that does, well, I hope, because I'm going a bit slower than I wanted. I'm going to tell you another form of actually producing hair on top of black holes that doesn't even require that, but it does require spin. Okay, but you can do, if you change sufficiently well the way that the field interacts with itself, you can hold it on to the black hole. It's just giving some pressure, right? I mean, in principle, you're free to build a wall around the black hole, right? And if you tweak sufficiently well the self-interaction potential, that's what you're doing.
Thank you.
Okay, any more questions? If not, let's thank Victor and Francesca again for their lectures. Then a reminder that today we have tutorials, like always, like the previous days, and anything else? Yeah, and dinner tonight, okay? 7:30 to 8. We start at 8, okay? The aperitives.